morning everybody. Hope you're all healthy and safe at home. We are moving on to the next section of our module 3, section 17.5, Cauchy-Riemann equations. So this is something very interesting about the complex functions and its analyticity and all. So let's see. What is the Cauchy-Riemann equation? Suppose the function f of z is equal to u of xy plus I into v of xy is differentiable at the point z is equal to x plus iy. Then at z, the first order partial derivatives of u and v exist and satisfy the Cauchy-Riemann equations. And what is a Cauchy-Riemann equation? It is dou u by dou x is equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. Okay, this is actually a theorem. That is, if we have a complex function f of z is equal to u of x comma y plus I into v of x comma y, and if that function is differentiable at the point z, then at that particular point the first order partial derivatives of u and v exist, and also dou u by dou x will be equal to dou v by dou y, and dou u by dou y will be equal to minus dou v by dou x. So this is a very important equation, Cauchy-Riemann equation, that helps us to determine whether the given function is, if the function is analytic or differentiable, then we can say that it satisfies the Cauchy-Riemann equations. Okay, so let's just first do the proof of this, and which will be and we can discuss about the converse, whether the converse is true or what, how can we use this theorem and all. So let's see how we can check whether the function, if it is differentiable, how will it satisfy the Cauchy-Riemann equation. Okay, so the function f of z is differentiable, right? So if it's differentiable, then f dash of z will exist, right? Its derivative exists. And what is the definition of f dash of z? F dash of z in terms of limit and all, we have done this. That is, it is nothing but limit delta z tends to 0 f of z plus delta z minus f of z whole divided by delta z. This was the definition. Now what I'm going to do is, I'm going to replace f of z by u of xy plus I into v of xy, and delta z is replaced by delta x plus I into delta y. Okay, now let's see what will happen to this particular equation. What will we get? We will get f dash of z will be equal to limit delta z tends to 0, and we have, instead of f of z plus delta z, we have to replace it by u and v, and delta z should also be replaced by delta x and I delta y. So it will be nothing but u of x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y minus u of xy minus I into v of xy. That is, wherever there is f of z, we replace it by u of xy and plus I into v of xy, and where there is delta z, we replace it by delta x plus I delta y. Okay, now what we are doing is, as we have discussed in the previous lecture, that the limiting condition and all, we must check carefully along which direction. It is not simple as in case of real, that it is coming from left or right. You have to check from which direction this delta z tends to 0. So first of all, I'm supposing that delta z tends to 0, okay, along a line parallel to the horizontal. That is, let us suppose that delta z tends to 0 along a line which is parallel to the y-axis or the imaginary axis. Okay, so in that case, what happens is we have delta z. This implies delta z will be nothing but delta x. That is, this delta y terms gets to be 0. Okay, or I can say delta y, there will be no change in y, that is delta y will be equal to 0. So what will happen to f dash of z? F dash of z will be nothing but limit, instead of delta z tends to 0, we have delta x. So delta x tends to 0 and u of x plus delta x comma y plus the variable v of xy. We'll write the I term separately, and this will be minus u of xy whole divided by delta x plus, I'm taking the I out common, okay, so it is I into limit delta x tends to 0 into u of sorry, not u, it is v of x plus delta x comma y minus, we have v of xy whole divided by delta x. That is, we are just substituting delta y is equal to 0 in this equation in terms of real and imaginary part. Now are you guys familiar with this expression? That is, what are we doing? We are tending delta x tends to 0. There is a change in x, but the y term it remains as it is. So it is actually the partial derivative of u with respect to x. So that is the expression of dou u by dou x, and we have the other one, that is dou v by dou x. Okay, so I hope this much is clear. Now next what we'll do, we will suppose that delta z tends to 0 in some other direction, that is it tends to 0 vertically. So when it tends to 0 vertically, what happens is delta z will be nothing but I into delta y, that is delta x will become 0. Okay, so if delta x is 0, what happens? Let us see what happens to f dash of z. Our terms will be limit delta y tends to 0 u of x comma y plus delta y minus u of xy whole divided by I into delta y, then plus I into limit delta y tends to 0 v of x comma y plus delta y minus v of x comma y whole divided by I into delta y. Right, so this is again similar to the expression of partial derivative of u with respect to x, but there is a I term which is extra in the denominator. In the second part, we can actually cancel out this I, right? So there will be no problem. Now to remove this I, will multiply the numerator and denominator by an I, right? So I square, we will get minus 1. So instead of multiplying and dividing by I, we will multiply and divide by minus I. So the denominator will become minus I square, that will become 1. Okay, so this is nothing but minus I into the rest of the term is actually the term of dou u by dou y, right, plus dou v by dou y. Okay, so here we are having two expressions of f dash of z, that is f dash of z is equal to dou u by dou x plus I into dou v by dou x, and also f dash of z is equal to minus I into dou u by dou y plus dou v by dou y. So f dash of z is common, it is same, so equating the real part and imaginary part correspondingly, we get dou u by dou x is equal to dou v by dou y, and dou v by dou x is equal to minus dou u by dou y, or dou u by dou y is equal to minus dou v by dou x. So that was our Cauchy-Riemann equations. So we have just now proved that if the corresponding function, complex function which is given to us is actually differentiable, then we can easily show that, or we can show that the Cauchy-Riemann equations will be satisfied. So just keep in mind the Cauchy-Riemann equation, that is dou u by dou x must be equal to dou v by dou y, and dou u by dou y must be equal to minus dou v by dou x. So the next slide is kind of important, and I want you guys to keep those points in mind. That is, if the function is analytic or differentiable, we say that the Cauchy-Riemann equations will be satisfied. It has to be satisfied, that is what we just now proved. The second one is, if the Cauchy-Riemann equations are not satisfied, then the function is not analytic. But just keep in mind that suppose the Cauchy-Riemann equations are satisfied, it need not imply that the function should be analytic. Okay, so just keep that point in mind, don't forget it. We can check whether the function is analytic by not just checking whether the Cauchy-Riemann equations are satisfied. We have to check extra conditions also. But if the Cauchy-Riemann equations are not satisfied, we can easily say, or we can confidently say that the function will not be analytic. Okay, but that does not mean that if the Cauchy-Riemann equations are satisfied, the function has to be analytic. Okay, that is not true. So just keep that in mind. So now this is actually we'll go for the criterion for analyticity, that is what will be the converse of the statement that we have made. So when we add additional condition of continuity of the real valued functions u and v, and also the partial derivatives, okay, all the partial derivatives, that is dou u by dou x, dou u by dou y, dou square u, and dou v by dou y and dou v by dou x, all these four partial derivatives must also be continuous. Then if the Cauchy-Riemann equations are satisfied, we can say that the function is analytic. Okay, so that's what the next point says, that suppose the real valued functions u of xy and v of xy are continuous and have continuous first order partial derivatives in a domain D. Okay, then if u and v satisfy the Cauchy-Riemann equations at all points of that particular domain, then the complex function is analytic. Okay, simply by saying that Cauchy-Riemann equations are satisfied, we cannot conclude that, or we cannot come to the conclusion that the function is analytic. We must check whether the functions or the real valued functions u, v, then their corresponding partial derivatives, all the four of them must also be continuous. Then only we can say that the given function will be analytic if the Cauchy-Riemann equations are satisfied. Now what we'll be doing is we will do a few examples which are given in your textbook, which will help you to understand more of our concept about Cauchy-Riemann equations, and how can we check whether that particular equation helps in finding the analyticity of the given function. So let's just see a few examples related to the same. So example 1, we are given the polynomial f of z is equal to z square plus z. Okay, first of all we'll convert them in the form f of z is equal to u of xy plus I into v of xy. Okay, so let's see what will happen. We have to substitute z that is equal to x plus iy. Okay, so z square would be x plus iy whole square plus x plus iy. So combining them we'll get f of z, or rearranging and getting together the real terms and the imaginary terms. So we get f of z will be equal to nothing but x square minus y square plus x plus I into 2xy plus y. Okay, it's not a very complicated process. It's just we are just substituting z is equal to x plus iy and forming the expression of f in terms of x and y, so that we can find the real valued functions u and v. So in this case u is equal to x square minus y square plus x, and v is equal to 2xy plus y. Okay, so what will be dou u by dou x? Dou u by dou x will be nothing but 2x plus 1. And what will be dou v by dou y? Dou v by dou y will be again 2x plus 1. So they both are equal. Now, not only the first condition, we have to satisfy the second condition also. That is dou u by dou y must be equal to minus dou v by dou x. So what is dou u by dou y? It is nothing but minus 2y. And what is dou v by dou x? It is again 2y. So there is a change. The value is same except for a change in the negative sign. So both of them are equal. So the function satisfies the Cauchy-Riemann equations. Okay, so the function is clearly differentiable. It is a polynomial function. We have no doubt in the differentiability of a polynomial function. So the function is differentiable, so it satisfies the Cauchy-Riemann equations. Okay, now we shall use the same Cauchy-Riemann equations to show that the function is not analytic, okay, at any point. That is the next example. That is, we are asked to show that the function f of z is equal to 2x square plus y plus I into y square minus x is not analytic at any point. So to show whether a function is not analytic, we will be using Cauchy-Riemann equations. Okay, if we are asked to show, then it is clear that any one of the Cauchy-Riemann equations will not be satisfied. So what is u here? U here is 2x square plus y, and it is v is y square minus x, right? So dou u by dou x will be nothing but 4x, and dou v by dou y will be, what will be the value? It will be 2y, right? So they are not equal, so we can stop right there. That is, the Cauchy-Riemann equations are not satisfied, so we can say that the function is not analytic. So that was the example of a function which is differentiable and hence satisfy Cauchy-Riemann equations, and a function which does not satisfy Cauchy-Riemann equations, and so it will be not analytic at any point. So just now we had stated the criterion for analyticity, that is, if the Cauchy-Riemann equations are satisfied, along with that if the functions is continuous, then we can say that all u real valued functions u, v and their corresponding partial derivatives are continuous. We can say that the function will be analytic. So let's just see an example related to that also. That is, it is actually stated as a theorem in your textbook. So using this theorem, how can we show whether the function is analytic or not? So let's see example 3. Example 3 states that the function given is f of z is equal to x by x square plus y square minus I into y by x square plus y square. So here u is x by x square plus y square and v is minus y by x square plus y square. So clearly this u and v are continuous at those points where x square plus y square is not 0, right? If the denominator is 0, the function is not defined. So excluding those points, at all other points the function is continuous, right? because it is clearly a rational function. I hope you guys remember that the numerator and denominator both are polynomials and all those stuff. So it is clearly a rational function, so you can actually check whether the function will be continuous at all points except where the denominator is not equal to 0. So now if we exclude that point, at all other points the functions u and v and their corresponding, we have to check whether the partial derivatives are continuous also. So what will be dou u by dou x? Dou u by dou x will be nothing but this is a u, so we have to use the quotient rule, and by applying that we get it as equal to y square minus x square divided by x square plus y square whole square, and that is same as dou v by dou y. And similarly we get dou u by dou y is equal to 2xy by x square plus y square whole square minus 2xy by x square plus y square the whole square, and that is equal to minus dou v by dou x. So in this case you guys can just verify whether it's true according to the quotient after applying the quotient rule and all. So the Cauchy-Riemann equations are satisfied. Also the partial derivatives and the functions are continuous at all points except 0. So the function f of z will be analytic in any domain which does not contain the point 0. Okay, so that's what we should we can say that the function is analytic at only those points where the real valued functions u, v and their corresponding partial derivatives are all continuous. Okay, so corresponding to that we can form the required domain. So that's it for today's session. Thank you. Stay home and stay safe.